Hey, welcome back to Graph Theory. In this video lecture, we're going to take a look at some material from the first section of Chapter 5 on multigraphs and Eulerian circuits. So you can see the goals of the lecture there in front of you. I want to introduce the notion of a multigraph. We're going to start with that. And then I want to tell you what I mean by an Eulerian circuit and an Eulerian graph. We're not going to prove, but I'm going to state the main theorem of the entire section, the characterization of Eulerian graphs. We'll give the proof next time. I'm going to actually end up proving a theorem that's slightly stronger than what's stated as theorem 5.1 in our book, but theorem 5.1 will follow from it. But today we're just kind of doing the prep work to give that theorem. We'll do it next time. So that's what the last bullet point is I'm just going to prove a lemma that's going to kind of tee us up for the proof of the theorem I'll give in the next video lecture where we'll wrap up this stuff on Eulerian circuits. All right. So let's motivate this whole notion of multigraph with the same problem that motivated graph theory in general, and in particular at the beginning of our course in January, and that is the Königsberg bridge problem. What was the Königsberg Bridge problem? Remember that this village in the former Prussia had these four land masses. In this diagram that you're looking at here, they're just denoted by the capital letters A, B, C, and D. So these four land masses, or diagrammatically, A, B, C, and D down there, they're connected by a total of 7 different bridges. And the question is, can you start somewhere? Can you start on one of the land masses and walk around in such a way that you cross each of the 7 bridges exactly once? That's one of the conditions. And I want you to return to where you started. Okay, so that was the Königsberg bridge problem. Can you take a stroll around this village, crossing each bridge exactly once, returning to where you started? So to diagram the problem, if we just denote the land masses by vertices and the bridges by edges, then you get this diagram in the lower left corner. And that diagram is not a graph. It's not a graph because the land masses might have more than one bridge. In fact, they do have more than one bridge connecting them. So the vertices in this diagram have more than one edge, and that's forbidden in a graph. Okay. Let's give a name to such forbidden edges. Let's call them multiple edges. So now we're allowing ourselves to draw more than one edge between the vertices in our graph, and the resulting structure is called a multigraph. Okay, so a multigraph is just a graph in which we allow multiple edges. If you want, we won't get super formal about this, but ask me if you want sort of a more rigorous definition. You know, because our rigorous definition of a graph is it's a vertex set together with a subset of the two element subsets of its power set. But I can give you a more rigorous definition. But for the purposes of this lecture, I think I just want to say that a multigraph is a graph in which we allow multiple edges. Just a couple of comments about these things. Every graph is a multigraph, but not vice versa. Not every multigraph is a graph. Graphs are exactly multigraphs in which every pair of vertices has at most one edge between them. We still have all of our notions. Order, still going to mean the number of the vertices. Size, still the total number of edges. Counting multiple edges. The size of the Königsberg problem is 7, the number of bridges. Vertex degree, same thing, but we count multiple edges. How many edges are incident with a vertex? Multigraphs are connected or not. Trails, walks, and so on and so on. Okay, so we already said that the Königsberg problem gives rise to this multigraph. Let's look at it. And yeah, remember what a walk is in a graph. A walk is just a sequence of vertices. Any 2 consecutive ones are adjacent, right? So same thing in a multigraph. And a trail in a multigraph is just a walk in which you never repeat any edges. All right, so you can repeat vertices and you can't repeat edges. Circuits are trails that end where they begin. So closed trails are called circuits. So they're different from cycles. Cycles, you can't repeat edges or vertices. But in a circuit, you can return to a vertex as often as you like, but you can't ever repeat an edge. Okay? So circuits that cover every edge in a graph are called Eulerian. An Eulerian circuit is a circuit in which every edge is traversed. And if a graph has an Eulerian circuit, it's called an Eulerian graph. Okay, so you can pause this and write it down slower if you want, but I'm just going to move on. So if I rephrase the Königsberg problem, I can just restate the problem. We've already said how the problem translates into this multigraph, and now the question is the multigraph Is the multigraph Eulerian? Yeah, can you walk along every bridge once, returning where you start? Is there an Eulerian circuit? Okay. Well, Euler answered the question by proving half of this theorem 5.1. Theorem 5.1 is a characterization of Eulerian graphs. And it says that a multigraph is Eulerian if and only if it's connected and every vertex has even degree. Yeah. So in particular, what Euler showed was that if you have an Eulerian circuit, then every vertex has even degree. And so glancing at this graph up here, we can see Euler's solution to the problem. This graph has vertices that don't have even degree. In fact, I don't think any of its vertices have even degree. But as long as so much as one of them doesn't, then the theorem says that you can't do it. So that was Euler's solution to the Königsberg problem. He drew this diagram and said no, that any such circuit would require that every vertex have an even number of edges incident with it. And since this graph does not, you're not going to find such a journey. Cool. Okay. So as I mentioned before, that and not today, but in the next video lecture, we're going to actually state and prove a slightly stronger theorem. It's just a little bit easier to work with, but it ends up applying theorem 5.1. So that's what we're going to do next time. I want to prove a lemma to kind of set us up for it this time, and then we'll shut this video down, hopefully keeping it a length where you watch the whole thing. All right, so I'm going to need a technical notion about a path called maximal, a maximal path. In a multigraph graph, it's a path that's not a subgraph of any longer path. All right, so intuitively, you just got to think about it. It's a path in a graph. You know what that means, or a multigraph. Paths, by the way, are never multiple edged. Right, a path is still a path. And when you have a maximal path, you just kind of can't extend it in your graph to be part of some path that has more edges on it. Maybe just to warm you up to the idea, notice that any diametral path, that is the longest possible path in the graph, would be maximal, but not vice versa. Not vice versa, because being maximal isn't about being longest per se. It means it's more like you can't be made longer and you're still a path. And sometimes, something can't be made longer even though it's not the longest. Here, I've got a little picture. That pink path that I drew down there for you is maximal, but it's not diametral. It's maximal, but it's not diametral. You can't put it in a longer path. You can't put it in a longer path. Remember, paths can't have cycles, so you can't add that edge that's not colored pink down here. Can't add that edge because then it wouldn't be a path anymore. Because a path can't return to a vertex. Good. Okay. So here's our lemma. The lemma says if you have a multigraph in which every vertex has degree at least 2, then you have to have a cycle. All right. So it's a fairly simple statement. You have a multigraph, every vertex has degree at least 2, then I can find a cycle in that thing. Okay. So we'll prove this lemma, and that'll tee us up for next time, and then we'll call it a day for this video lecture. So let's see if we can walk through the proof together. So take a maximal path in your graph. They have to exist. Maybe it'll be diametral, but whatever, just take a maximal path, take a vertex on it. Kind of follow along in this picture down here. The picture is not a proof, but it's a good diagram to follow along. So I take some maximal path, pick a vertex on it that's a so-called endpoint. You know what I mean by the endpoint of a path, but if you want to be slightly more rigorous, I mean in the subgraph of this path, the degree of this vertex is 1. So you're ignoring everything but the pink edges, then U has degree 1. So paths have 2 such things, pick 1. Now we're going to use the maximality. All right, we have a maximal path. So for every vertex in its neighborhood, let me remind you what the neighborhood is. I just mean the vertices that are adjacent to U. For every vertex in the neighborhood of this U, this endpoint of our maximal path, those vertices all have to be on this path. That's what I'm writing there. They all have to be on the path. It's certainly true in this picture, but look, if you had a vertex adjacent to it that wasn't on the path P, then P wouldn't be maximal. we could P is a subpath of a longer path. Yeah, if U has another vertex adjacent to it that's not on P, I don't have to make new ones in any way. If you could leave U again, not along P, so on an edge that's not in the path P, then this path P wouldn't be maximal. It's kind of what maximal means. Yeah. So I'm going to get rid of those things as you're watching, but that's what my claim is. For every vertex in the neighborhood of this U, this endpoint, that vertex is on the path. That vertex is on the path. Here, I'm going to change something down here as we go. Okay, so what's my next claim? My next claim is that because the degree of U is at least 2, right? Every vertex in this graph has degree at least 2. Only one edge along the path P is incident with U because U had degree 1 in P, right? So just like in the picture, only one pink edge is incident with U. There has to be a non-pink one, right? There has to be a non-pink edge because the degree of U is at least 2. And we've said that anything adjacent to U, so because along that non-pink edge, the other vertex is in the neighborhood of U, and we've said everything in the neighborhood of U is on this path. So there has to be such a vertex, yeah. But moreover, the edge E, that messy handwriting says, the edge E between U and that vertex, I'm going to just kind of label it here in my schematic picture. That edge is not on P. The edge can't be on the path P because that vertex V is on the path P, right? And we're saying that this edge is not the path edge that goes into U. So this edge E can't be on the path as well because only one path edge goes into U. The degree of U on this path is 1. That's what I'm trying to spit out. So that's all I want is an edge E between U and V that's not on P. Okay? And now I'll just switch colors to indicate as I'm drawing it. So this is the portion of P from U to V. So I'm going to just sort of shade that in green. The portion of P, sorry, from U to V. I went the wrong way. From U to V, because I know there is such a portion. V is an element of this vertex set of this path. Together with this edge E that goes back to U, that's your cycle. Okay, so next time what I'll do is just start right away by stating a theorem, an if and only if theorem that characterizes multigraphs, and the characterization that's in your book is theorem 5.1 will follow from it. And then we'll talk a little bit about some next best thing to Eulerian cycles are called Eulerian trails. That'll wrap us up for section 5.1. Okay, so I'll see you in the next one.